So I thought that I will speak a little bit about measurement because my talk will be dealing about weak measurement. So I talked a little bit about strong measurement, and this is one aspect of quantum mechanics which really is fascinating. So even now, many aspects, many things about it are ill understood. So I will use this whiteboard. We have encountered in the morning session with bosons and fermions. For example, this electron, proton, these are all examples of fermions. Bosons like photon, this light particle is an example of boson. So all of these objects are characterized by wave function. So this wave function psi has two parts. One is spin and one is space part. So spin part, for example, so the wave function has this kind of a structure, product structure, so that the space and time part separate out, and then we have the spin part. For the electron, all of us know that the spin has three components, Sx, Sy and Sz. They were introduced in parallel to angular momentum Lx, Ly and Lz. This we have understood, right? It comes from R cross P, classical to quantum. Spin is completely quantum. And we found that these objects don't commute. So we have to simultaneously, you cannot diagonalize all of them, right? All these operators. So what we do is, for example, typically we will take Sz, which is in the form of S bar by 2, 1, 0, 0, minus 1, already in the diagonal form. And the corresponding eigenstates are the spin states. For example, 1, 0 is our qubit. All of us use it as qubit. Sometimes we'll call it 0. Sometimes we'll call it off state, different kind of notation, depending on if you are, you belong to physics or you belong to computer science. 0, 1 is down, 1, this other qubit, and down. So now, so you see the role of measurement. So that is very, very interesting. So first let us deal with this finite dimensional Hilbert space. So please remember that in this, although in quantum mechanics, we have been dealing with it since 1925-26, but in quantum computation and quantum information theory, so far we are comfortable only with this. That too, two particle state with qubit. Beyond that, as you saw in Professor Patti's talk, GHZ, W state, which are three particle state comprising of this object, they are still not very well understood. So we have understood in two particle state, their property, their entanglement. Measurement, for example, we thought we have understood measurement, but you see, people like Aharonov, they come up with very, very amusing scenarios about which measurement I'll be talking about. So there are many aspects of quantum mechanics which are still not very clearly understood. So, so let me point out, for example, see this, if it's a classical object, a classical particle, we have x, y and z, right? So suppose the spin is along the z direction, 1, 0. Now whenever you measure in quantum mechanics, you first choose the basis, which direction you are measuring. So if it is along 1, 0, if I measure along 1, 0, namely choose z direction as the measurement basis, I have two states, 1, 0 and 0, 1, I will find that the particle is along this direction. It is not along this direction. But suppose I prepare my particle along 1, 0 direction, along this direction. Now I measure along the y direction. What do I find? If it's a classical particle, I will find a given measurement will give me 0 because the particle is not there. Is that clear? Right? We have been all the time telling that it's a classical particle. If it is along this direction, if you measure along y, we should find 0. But look, in quantum mechanics, what we find? So if we want to measure, so it is convenient to make measurement along x direction. Why is that? Because Sx is nice. Sx is in the form of S bar by 2, 0, 1, 1, 0. The eigenstates are 1, 1, 1 by root 2, and 1 by root 2, 1 minus 1. So if I want to measure along the x direction, first I have to choose my basis. This is my basis. Then I have to expand this object 1, 0 in terms of that basis. What is it? It is 1 by root 2 times 1 by root 2, 1, 1 plus sorry, I put it this way, 1 by root 2, 1 by root 2, 1 minus 1. And you can see that 1 by root 2, 1 by root 2 is half. If you add them up, it will give you 1, 0. Right? So I have taken normalized basis. This 1 by root 2 is for the purpose of normalization. Now you see, when you measure, this is 1, 1. So if you measure along the x direction, what will you find? You will find that after the measurement, the particle is either along this direction or that direction, right? Because this 1, 0 particle is made out of these two. One of them is along the plus x direction, other is along minus x direction. So according to Niels Bohr's or the Copenhagen picture, after the measurement, the state will collapse. So it will collapse to either this one, 1 by root 2, 1, 1, or to this one, which is 1 by root 2, 1, minus 1. So this is really the quantum aspect. So there is no classical analog that a single measurement is producing for me either the state which is along the plus x direction or a state which is along minus x direction. So this is really quantum. There is no classical analog because classically, if the state is along 1, 0 direction, if I measure, I should find 0. But quantum mechanics is giving this. So the fact that they are equal mixture, 1 by root 2 is the amplitude, probability is 1 by root 2 whole square, which is half. So if I do large number of measurements, like 1000 measurements, 500 times I will find the state is this, other 500 times this. So now you can see how classical picture emerges, because if you take average now, you will find average of the spin, which since the state is along this direction, if you measure the spin value along the x direction, you should find it to be 0. So if you do average value after large number of measurements, you find that half of the time the particle is along plus x, having half spin half, other half along minus x, having spin minus half, so the average is 0. So this classical picture that the spin is pointing along z direction, hence there is no value of spin along x or y direction, emerges after large number of measurements. But a single measurement is going to produce for you one state, either this or that, and that is a completely quantum object. It has no classical analog. So the measurement has collapsed the state. So first of all, I have chosen the basis state. So all these things will be required for my talk. So that's the reason I am emphasizing. So first you have to identify the operator whose eigenvalues and eigenvectors you want to measure. So eigenvectors are the basis. Once you choose your basis of measurement, you have to take your state, expand amongst them, find out what kind of weight factor which comes in here. So measurement will produce those kind of states with the appropriate weight factors. This is what we learned from here. Now question is it a very simple thing? Can it be used? Answer is actually this simple fact has been used. And there is an entire paradigm of quantum computation called measurement-based quantum computation, MB, measurement-based quantum computation, which has emerged that only through measurement you can actually implement quantum computation, which is based completely on this, that the fact that a measurement collapses the state to a suitable one. So that can be used for quantum computation. So fine. So single particle. How about this object psi xt? As I told you, that we are not very comfortable, although we have solved hydrogen atom, we have solved, for example, harmonic oscillator, but still we are not very comfortable in characterizing the entanglement property of this part. We have only learned how to use the Gaussian part. So you have seen, for example, yesterday, Professor S.M. Roystock, the apparatus which measures the spin, that was modeled by Gaussian. So that much I will need. So my talk will deal with the spin part and the part, the space part, which will be Gaussian. So psi x part, which will be Gaussian, something like exponential minus alpha x minus beta whole square. So let me write it in this way. Sigma is the width, beta is the location. Now this kind of wave function, shifted Gaussians, so physically this kind of wave functions appear in description of laser. So this precisely describes the laser. It's a completely classical state, which Suranjan emphasized in the morning. Linear superposition of that is the so-called cat state, which I will be using. So this is one object which we understand quantum mechanically. And you will be happy to know that, this so-called Gaussian class of states were studied and quantified by Professor Simon. It's a very remarkable paper. So Gaussian part we understand clearly. So that's much I will be needing. Now, the second part is, for example, again question comes to measurement. So in general, if you have an unknown state psi for a single particle case, you have seen that you can write it in this way. So again, a measurement will collapse the state to either 0 or 1, and with a probability either alpha mod square or beta mod square. Normalization gives me alpha mod square plus beta mod square is equal to 1. So this is our single particle state, that the measurement collapses to this. Now it comes to two particle state. In the case of two particle, the simplest one is Bell state. For example, two particle up down, let's say minus plus minus, down up by root 2. Again, a measurement, for example, this could be particle 1, particle 2. So one measurement will produce the fast particle, for example. Now I have to choose my basis. Suppose I choose to measure the fast particle in the up-down basis. So the result would be half of the time it could be that the fast particle is up when the second particle is down. The other half would be the fast particle is down and the second particle is up. Okay? So this is the correlation comes because of entanglement. That the fact that you are entangled, that manifests here, that the fast particle when it is up, second particle is down, and when the fast particle is down, second particle is up. So this kind of things which comes because of this quantum correlation finds application in quantum communication and many other tasks. So again, measurement has collapsed the state. Choice of basis is important. So with that, let me now get into this measurement and particularly weak measurement. So you can stop me anywhere if you have difficulty. Okay. Okay. So this I have emphasized that quantum mechanics measurement plays a very fundamental role. So now the thing to appreciate that there is inherent uncertainty in quantum mechanics. That part of it comes because of technology. For example, in morning time again you heard a talk about precision, determination of quantum metrology, precision determination of parameters. If you improve the technology, you can determine parameters more accurately. But more important point is that there is some inherent constraints in the theory itself. It gives some uncertainty arising because of non-commutativity of operators in quantum mechanics. So this is the thing which we should be careful. Unlike classical mechanics, quantum mechanics has inherent uncertainty. Okay. So when we are doing metrology, we are trying to find weak parameters very accurately. There are two techniques which have emerged, which in the morning time this Heisenberg limited measurement was emphasized, which uses novel class of states like the so-called compass state, cat state to very accurately estimate parameters like displacement in coordinate, displacement in momentum. Similarly, values like angular momentum and things like that. And it has also found experimental verification that this kind of quantum states can be used for sensitive parameter estimation. This weak measurement is a recent concept which has emerged through the work of Aharonov, Weidman and that emerged only in 1988. Still not very well understood. Lot of experiments are beginning to appear, and it's quite an interesting thing. You can use it for estimation of for amplifying very weak values. Like for example, recently they found the so-called photon trajectory and this spin Hall effect, photon spin Hall effect, which is a very weak effect. It was amplified using this. So as I will show you, taking very simple examples, that both these things they depend on interference. In the morning, it was emphasized that this Heisenberg limited measurement depends on interference in the phase space, which was illustrated using the Wigner function. It was shown that because of interference effect, there are sub-Planck structures which actually gives the power to this kind of states. And I will show you weak measurement also relies on the same thing, okay, except that both of them use the same kind of quantum state, but in two different regimes, two opposite regimes. So that's what I will emphasize here, and I will show it to you here. Now, in this Heisenberg limited measurement, the state was used, the measurement was carried out on the state, the disturbance was put onto the state. For example, state was shifted by a slight amount. Then overlap was taken with the original state, and it was shown that the slight shift will produce some shift in the zeros of the wave function or in the phase space that can be measured. Here, on the other hand, what happens that we have a pointer which is measuring the thing, like for example, the kind of thing Professor S.M. Roy was telling in the morning, and in that pointer, the location will depend on the interference effect. So here the location of the pointer, that will give the value. Here the location of the zeros, that was giving the measurement. So there is a slight difference there, but both of them rely on the same kind of interference effect to produce this novel things about metrology. Okay. So again, Cass states and the compass states, they are the ones which play a crucial role, and they show this they are quantum in nature. For example, in early 90s, they were studied largely through their statistics, the so-called subposition statistics emerges here. Then it appears more naturally through the Wigner function. There are negative areas which shows quantum nature. More importantly, you will find zeros of this cat and compass states, they have a definite structure in the as shown in the Wigner function. So we are concerned with this kind of spin variables, dichotomic variables, okay? And for finding carrying out this weak measurement, we will use again the so-called cat state. They will appear as the pointer state, namely the location of the pointer of the experimental apparatus will come through this cat state. As I showed you, the displaced Gaussian, that beta, the location where x is located, namely the Gaussian peaks, that is the pointer. So the pointer direction will tell us about the weak value. In both the cases, this dichotomic variable will be like a two-level system. Either it could be spin, or it could be polarization, or it could be two atomic levels. And this other thing will be a Gaussian, shifted Gaussian, which will be representing the measurement apparatus. So now, let us now get into more specifically. Okay. Just to point out once more that the sub-Planck structure was first observed, observed by in the phase space by Wheeler and Sly. It was observed again independently by Jurek. But nice thing about Jurek is that he pointed out that you can make use of it. You can make use of it to understand this, this so-called, particularly he made use of it for parameter estimation, and which was later on experimentally verified. This idea has been experimentally verified. Okay. And it makes use of this negative region in phase space. So this has been shown in the morning, so let me not get into it. And Surendran has showed you this nice plot. He has explained that the sub-Planck structures appear in these domains, and they appear through the interference effect. Okay. So now, this coherent state, again, just to repeat, she has pointed out in the morning that coherent state is classical. It gives you parameter accuracy up to 1 over root n, the so-called short noise limit. This can be improved to 1 by n through the so-called soft noise sensitivity that can be achieved through the use of cat states, and that much like Heisenberg limited sensitivity, weak measurement also uses that fact. The soft noise sensitivity is used also for the weak state. Okay. So now, as I mentioned, this is a new concept. It emerged through the work of Aronov, Albert, and Weidmann in 1988. Subsequently, Sudarshan also had pointed out the same thing. So now, what is this weak value? It is actually, in this measurement scenario, the empirically measured value that is called the weak value. of an observable can be it can be puzzling in that it yields results going beyond the eigenvalue spectrum of the measured observable. Let me emphasize this point. That, I will emphasize it more clearly as we go along. That, all that I will need to emphasize this point is like a Stern-Gerlach experiment. So, in the first few chapters of quantum mechanics, we have been told that the spin variable, that is a dichotomic variable, taking values only up and down, can be illustrated through a very simple experiment originally due to Stern and Gerlach. What they did, they took the silver atom. I will show you that experiment very clearly. And electrons were excited from the silver atoms were excited. The last electron being the silver atom being a closed shell with one electron, behaves like a spin half particle. So, in the presence of a non-uniform magnetic field, it experiences force, and on a silver screen or on a photographic plate, it hits at 2 points. So, that is what I mean by dichotomic variable. And the displacement depends on the spin value being up or down. Now, what I am mentioning here is that in this weak measurement, although we are doing a similar kind of measurement, you will find that the displacement or the measured observable, the location of the Gaussian, can be far, far beyond the eigenvalue spectrum. So, as I go along, this part will become clear. So, that is the reason why it is so effective in amplifying weak values. Okay. So, there are two uses of this weak measurement. One is, and I will highlight several of them here, it actually brings more insight into many conceptual quantum paradoxes. Some of those things I am not very familiar. I will point out to you, if so, you may play around later. There are many of these paradoxes which are existing, and it really brings the physical clarity to those paradoxes. The other one is more pragmatic, more practical. They have been used experimentally to find very small spin Hall effect, beam deflections, very small beam deflections, and this trajectory of photons, those things have, for which this has been used. Okay. So, the goal is to show that sub-Planck structure plays a key role, and this Heisenberg limited and weak measurement, they are complementary to each other. So, both of them make use of this CAD state, superposition of two coherent states. Alpha, you see this alpha is displaced Gaussian. So, as I mentioned to you, this coherent state describes laser, just a shifted Gaussian. And there is a phase factor here. So, this phase factor will play a very key role. Okay. So, now, just to connect up with what I am trying to do, so I am using this result which Surendra showed in the morning. Let this coherent state, also the CAD state, be displaced by small amount. You see, this is like a momentum displacement, because exponential Ix times delta. Ix times p is the momentum. So, here delta is like a shift in the momentum, slight displacing momentum. What we find that if we exactly compute the overlap function, we find that it is having this kind of structure. There are some oscillatory factor times cosine, and there is some integral I. What is this integral? This integral is given later, is the overlap function. It's a very important point, overlap of these two. And as you can see, it's a superposition of two Gaussians. So, if I take the psi, psi star and psi, it will obviously involve this overlap of plus and minus. So, that is what it is. And this overlap function plays a very crucial role. You can see this overlap function, depending on the parameter values, could be 0 or could be 1. And it will lie between 0 and 1. What I will show you, that in one case, it will be, when the overlap is maximum, then it will lead to this kind of weak measurement. And when the overlap is minimum, it will lead to sub-Planck structure. Okay. So, this I is equal to 0 is the sub-Planck structure which Surendra was mentioning in the beginning. And when in case of I close to 1, I will show you that kind of interference would give rise to this weak measurement scenario which I am talking here. So, let me again go back to here. So, you can see, for example, here, if I is equal to 0, you see these terms are all gone. What is surviving? Surviving is this object, this cosine factor. Off diagonal terms are gone completely. Only diagonal terms are surviving, and one interference term. Interference term, the so-called dominant interference term, which is surviving. And you see that has a cosine factor. So, you can see overlap function, there are zeros, which was emphasized in the morning. And these zeros are the ones whose locations will give you the parameter estimation. So they appear here. So to determine it accurately, you need to kill off these terms. So the I has to be 0. We have to take these cat states with suitable parameters so that I should be close to 0. Then only the sub-Planck structure will manifest and the Heisenberg limited parameter estimation can take place. Fine. So let me go to the other one and let me show how I is equal to 1 leads to the so-called weak measurement. Okay. Okay. So first of all, even if the, so what we learned from our strong measurement? In the strong measurement we saw, we have superposition of states. A measurement leads to collapse of the wave function, okay, and through which, a large number of measurements gives us the average values. And you will see here that this, the weak measurement, on the other hand, it will allow you to extract information of quantum system in the limit of vanishingly small disturbance, just like the kind of small shift which was mentioned in the morning. Okay. Now, this pointer state which I pointed out, this Gaussian, shifted Gaussian is a pointer state. Location of the pointer is that peak of the Gaussian. So as I mentioned to you earlier, in case of standard Stern-Gerlach experiment, as I will show you again explicitly more later, depends on the eigenvalue. Whereas here, to emphasize once more, we will be far, far away from that, and that is what will distinguish between the strong measurement and the weak measurement. So there is one step we involve in case of weak measurement which was not there in the strong measurement, and that leads to this kind of nice results. And this beyond the eigenvalue range, that's what you should remember. Now let us see. Now this Stern-Gerlach experiment I have been telling you many times. So what is it? It's a very beautiful experiment done in the early days of quantum mechanics. Very emphatically pointed out that there could be the so-called dichotomic variables. People are not believing that spin degree of freedom can be 1, 0 or 0, 1. So this silver, and you see silver closed orbit, the last S1, S has 1 electron, so it almost behaves like an electron, namely a spin half object. So from you heat up from the oven being the silver, there is a collimator, nice silver particles comes carrying spin half, unpolarized, because now half of them of one direction, the other half in the other directions. So now there is a magnetic field. Now you know that the electron, the spin half will interact as minus mu dot B. There is non-uniform magnetic field, because of which there will be force. Now if it is plus half, it will go this way. If it is minus half, it will go this way. So now, what happens? Now you put a screen. In the screen, you will find a lot of them will be hitting here, a lot of them will be hitting here. That is how the dichotomic nature of the variable comes out. So you can see when it hits, this kind of things comes out. This is really a Gaussian. This is like a pointer state. So there is a detector here which is detecting it. And you see it has a Gaussian spread kind of thing. So the location is like your Gaussian. So in the von Neumann theory of measurement, when you do a measurement, the system and the apparatus get coupled, and the apparatus location is determined by the system eigenvalue. So here, depending on the strength of the non-uniformity, there will be a distance. The distance will be more or less. But once non-uniformity of the magnetic field is fixed, these locations will depend on the eigenvalues, plus half here, minus half here. So fixed magnetic field, this location is fixed. If it is half here, it is minus half here. If it is polarized, of course nothing to do. It will shift, either go this way or that way. If it is unpolarized, namely made up of plus and minus, then only this quantum measurement will come into picture. It will collapse it to either this or that. So this is what you see, and now you see the original object without magnetic field. You see only in the center. The moment there is magnetic field, it shifts, and there are two Gaussians here. Okay. So unequivocally telling that indeed this is a dichotomic variable carried by silver. Okay. So now let us get into this weak measurement. So what we need, like in the case of strong measurement, you have to prepare a system in certain state. This is called pre-selected state. Like either spin along the z direction, spin along the x direction. How do you prepare it? You prepare it by putting a magnetic field or by measurement, because as you know, measurement collapses the state. By some means, you have to prepare the state. So the pre-selection is the first thing to do. So now we have to identify which observable we are measuring. So the observable is O. For example, it could be sigma x or Sx, Sy or Sz. So one of them you have to fix. So then Then what you have to do is, I will show you more explicitly, that you have to allow for some time that there will be some interaction between the system and the meter. So you have a Gaussian times your state which you have selected. You will allow the system and the apparatus to interact. If there is no interaction, information about the system will not go to the apparatus. So this interaction has to be there. Here, what is the interaction? You will soon see that the interaction will be exactly like the Stroud-Zerlach kind of experiment. So through it, system and apparatus will interact. So there is a period of interaction that we have to keep in mind. Otherwise, information about the operator will not go to the pointer. Now, this is the crucial thing, that after that in the strong measurement, you had a detector, these fellows go and hit at some place. Before that, in case of weak measurement, we do something more. We select out another state. So that determines the so-called weak value. So this is the crucial difference. You will just keep this in mind, and I will show you more explicitly. Okay. So what is the formula for this weak value? So as I told you that the initial state has been chosen, some initial state, operator has been chosen, and that last point, that post-selection, some state has to be chosen, chi f. So the weak value is given by this. So expectation value of the operator between the pre-selected and the post-selected state, and the overlap of the pre and post. Now this is the one which will be determined by your pointer. That pointer location will be giving us this. And you can see if this chi in and chi f, if they are near orthogonal, this could be close to 0. 1 over 0 would be infinity. That is the reason the shift in the pointer state would be very large. So that is what will come out. So let me give you now some example. So this, let us say that we have prepared our in state as a linear superposition of up and down state with fixed alpha and beta. This alpha beta we have to give. If alpha beta is unknown, this is an unknown state. But in our case, we have to take a known state. So alpha beta is given to us. So this is our chi in state. So final, after allowing the particle to interact, I have to select this, the so-called post-selected state, which is chi f. That is, let us say, only the j state. The observable is sigma x. So these are the things. Now you can very easily compute. If you compute, you will find that sigma x weak value is given by beta by alpha. Now alpha is small. If alpha tends to 0, if your initial state is such that has a very small component of cross z direction, this weak value could be infinity, very, very large. But then what happens? You find that the overlap between in and f, that is also very small. So finding, what happened? Yeah, so the overlap is also very small. What it tells you, that when the weak value, for measuring the weak value, when you are doing this pre and post selection, once you pre-select the state, and if you want to really have a strong weak value, the overlap is very small. That's when finding this chi f is very, very small. So to do the weak value, you have to do a very sensitive measurement. So that is what it implies. Okay. So let me tell you a bit more mathematically. So the kind of approximations what I did, what I told you, that amounts to taking this state, this coherent state, expanding it up to the first part, adding them up to find the so-called cat state in this approximation. Again, using this approximation, that this first thing can be exponentiated. So this is what the approximation of Aharonov, Weidman, and the Alfred is. So you find this psi c, the cat state is in this form, and the shift of the motor of the state is at this location of the weak value, beta by alpha being the weak value. So these are the kind of approximations which are required to justify the measurement in the case of the weak value. Okay. So now there we saw it is I. But I is not a big problem, because in the real space, if there is an I, if you go to the Fourier transform, you find that the momentum has been shifted by this amount. So what we infer from here is that the weak value indeed gives a shift in the momentum, a large shift in the momentum, but as we saw, this alpha, which is the overlap, is very small, because only if alpha is small, this fellow could be large. So what it is doing is that from the original beam through the post selection, it is selecting out the so-called high momenta particles. But the high momenta particles are very few in number. That's the reason this alpha is small. But if you can detect them, you get a large momentum shift. So that is the physical interpretation of weak measurement. Out of the wave functions, you are selecting out the so-called high momenta fellows. Their probability is small. But if you find them, then for those particles, you find there is a large shift, huge shift in the moment, in the pointer direction. That's what the thing that emerges physically from here. So more explicitly, how do you carry out this? Same Stern kind of apparatus, except that for post selection, you put another magnet here. So you have prepared your state originally, that the pre-selection, that alpha beta which I took, which was cosine theta by 2, sin theta by 2, that state was pre-selected here. Once the state is selected by a strong measurement, you allowed that state to evolve through this interaction. This is the phase where the information about the pointer state and the dichotomic variable gets coupled. Then you do a strong measurement, that sigma z measurement, as I mentioned to you. Once you do that, then this is your pointer state whose location could be far, far away from the origin. So this is the apparatus in which it has been realized. So now, you start more mathematically, you start with the pointer state and the in state. As I told you, in state is alpha beta, but in this case, we have chosen them to be cosine theta by 2 and sin theta by 2. So in the beginning, it's a product state. So the pointer state is a Gaussian, and if you take the Fourier space, you will find this I will go away. It will be a momentum localized at some point, because Gaussian's Fourier transform is Gaussian. So after some time, then you allow them to interact. When you allow them to interact, you can actually solve it explicitly and exactly. Interaction Hamiltonian is of this type, mu sigma dot b. You choose a magnetic field of this type to make your life easy. Now once you do that, you find that after time period tau, the wave function is no longer a separable state. Initially it was separable, it gets entangled. So this plays a very crucial role, that the wave function in between gets entangled. So the psi plus with x state and psi minus this is an entangled state. So the entangling property of the interaction plays a very crucial role in weak measurement. So then, and in the process, you have to solve this kind of equation, which is not very difficult. And you see, the wave functions have these natural Gaussians, so which are very useful as pointer states. So the pointer states emerge because we have this kind of equation. So this plus state corresponds to the sigma x, minus state corresponds to sigma x with plus half and minus half. That shift is here. One place is, you see, minus, and the other place is plus. So now, and again you see the overlap which I was mentioning, psi plus and psi minus. So here it has to be close to 1, otherwise this scenario will not work. So now this last one is the one which did this post selection, namely sigma z was separated out. But what it does, once you see, this is what we do. We take that wave function, separate out this object. Once you separate out that object, you have a wave function of this type, and where you see the shift is proportional to the momentum, and it could be in principle very high. Okay. So to be precise, I can write it the Fourier transform in the form which I had shown you earlier, and this weak value appears here, and this is exact, there is no approximation, and appears in exponential, giving rise to a shift in the momentum which is quite huge. And here everything is exact, I have not taken any approximation. Okay. So now, since many of you are curious in these quantum paradoxes, let me highlight for you some of the paradoxes where, okay, these are the, what happened to now? In this foundation theory, it plays a very key role. I have no expert in this. My postdoctoral fellow Alok Pan, who is now in Japan, he likes this kind of thing, so he has made it for me. So he's saying that a lot of this kind of, what are the, anyway, this already here that, for example, if a state is given, measurement will give you either, if you are measuring the x state, you will find 1. But suppose if it is not quantum mechanics, if things are predetermined, then you can actually get half. But we know that classical realism is not true, quantum mechanics is true, but there are many, many paradoxes which arises. So, okay, these kind of things I don't quite like. Okay, see this thing, this AAD, namely the weak measurement, arose after some initial observations, again due to Aharonov Bohm and some other author, I forgot his name. What is that? The question they asked in 70s is this, that suppose in quantum mechanics, let us, can we think about the dynamics when the initial state and final state are fixed? You see, the initial state is the final state, and there is an initial state. In between, you have done a measurement. What happens to this kind of scenario? So, there is a time period before which you are some state you started with I, and a final state F, and in between you have done a measurement, some state J has emerged. So, this kind of evolution, they sort of inquired, and that led to many of these paradoxes. What are those paradoxes? So, this is the reference, Leibowitz, Aharonov, Bergman, and Leibowitz. So, there are many, many paradoxes. Seaborg's paradox, which I am not very familiar, but apparently they are very useful. There is another paradox, Hardy's paradox. Again, measurement, initial measurement, final measurement, in between some evolution. So, that are becoming very, very important. What are the other one? Okay, this new, this is some Josa and Popescu paradox. So, these kind of things are interesting, because what they show you, they can sort of separate out degrees of freedom. One place you will observe the spin, other place you will observe the charge. So much like this, as if the physical degrees of freedom you have removed and manifested it somewhere else. So, again through very clever measurements, initial and final measurements. So, the so-called Cheshire cat, this, this kind of thing people have used, that some place there is a cat's grin, which is the, cat is smiling, some place cat's other degree of freedom is there. They are all very clever measurement scenarios involving this kind of idea, that there is a pre-selection, there is a post-selection, in between there is weak measurement. Pre-selection, post-selection, in between there is this weak measurement. That's what has been used to produce these kind of things, and many of these things have been seen experimentally also. So, these are very interesting things. So, I will not get into any of these details. So, I think I will stop here. So, this has been done in collaboration with Dr. Alok Pan, who is a JSPS fellow now in Japan, and with Anirban Choudhury, who is here with me right now from IISER Pune. And there are many of these things which I still don't understand. I am new to this. So, I hope something I have brought to you to arouse your curiosity. Thank you.